Could you put up a picture of the structure that you analysed again? It doesn't matter which one, but that shows the gain and the loss of a single unit cell of the structure that you're analysing.
You mean this one, or you mean the bilayer, the homogeneous?
So keep going back. Yeah, I'll say.
Sorry.
Keep going back.
Okay.
In your slides, I'll say.
Okay.
Yeah, that'll do, that one. So,
okay.
So can I just clarify? Is it just a single bilayer that you're?
It's a single bilayer. It's a single bilayer which is parity-time-symmetric only along the Z.
So by paraxial, the definition of paraxial means near normal to the interface.
No, but we have not used paraxial approximation here.
No, I understand that. But then my next question is both the gain and the loss regions are actually isotropic.
Yes.
So I'm a bit surprised that the only way that anything can happen as you deviate from normal incidence is for in some sense for it to be sensitive to the interface. There's no anisotropy in the system otherwise.
It is sensitive on the interface, and this sensitivity is reflected on the fact that we don't have now the eigenpolarizations. They are not the left and right polarizations, but all the transmission and reflection. Let me show you the scattering matrix. Okay, all these components that I have put here equal to 0, they are not zero anymore.
Yes, but that must be pure. But that must be purely a function of the presence of an interface. It's the individual media are still isotropic.
It's only the presence of the interface.
So I mean, is it possible that there's some kind of surface mode that is formed as you move off axis?
There are surface modes also for normal incidence. There are some special case where we have surface modes with quite high amplitude, but still we are on the way to explore, let's say, this type of modes.
Okay, thank you very much. Very nice talk. I'm afraid I actually have to go, so I'm not being rude, but it was.
Thank you. Thank you.
Thank you very much, Martin. Actually, following up Martin's question, so now what would happen, in your opinion, if you would have these two layers, but they are anisotropic and they respect this PT-symmetry requirement? So epsilon, mu, and kappa, now they are rank 2 tensors, matrices.
That's a kind of difficult.
It remains homogeneous. It's anisotropic, but homogeneous.
I don't think that I can.
Obviously.
Besides, I'm not sure that I can. I'm not sure that I can conclude, let's say, from what I know. Certainly, all this stuff will not be zero, as it happens in this single interface.
Of course.
And of course, you will have all the cross-polarized components, and then you probably have more.
Because obviously your unitary relation would still hold. It would be still the same because you would have the exact same arguments for your theorem. I mean, this.
Yes. That's true, but let me think. I don't think that I can reply with confidence.
But I think it's an interesting direction for you because obviously, like you said, these off-diagonal blocks, they would light up now. Something there would happen, and you would have a further,
We'll have further effects and more interesting effects. That's true. So This probably will be a next step for us, because in the case of metamaterials, for example, it is what happens actually in the realistic structures. They are anisotropic in the.
They are, yeah, for the split rates and so on. When you model it by anisotropic, I mean, it is, yeah. Okay, so please, people, come forward with your questions. You know, it's a unique opportunity to ask even, you know, naive questions like me, I mean, to Professor Kafesaki. Yes, please,
Hi,
Paloma.
Sebastian. Can I ask something?
Yes.
Yes, I was wondering about your diagram where you go from the PT unbroken to the mixed broken phase. So, first, if I understand correctly, your mixed phase, that will mean that one of the polarizations will be in the broken phase, and the other circular polarization will be in the unbroken phase. So you can get a CPA or one of these effects only for one polarization. Is this correct?
It's not one polarization. Actually, it's not the eigenvalues. Okay. They are not single polarization. The eigenvalues, the eigenvalues correspond to wave that it is for one eigenvalue is left wave from this side and right incoming from the other side, and the same for the outgoing. So that each pair it contains both polarizations.
Okay, so it's more complicated than what I was saying.
Yeah.
Okay. So then do you have an intuition of? But what will happen physically if you input your system with one polarization and you are in the mixed phase?
If you are in the mixed phase and if you plug in with one polarization, then it will happen. Okay, you will have, if you have small angle, then you will have transmission and reflection like is shown here. You enhance. If you go here, for example, if you go with a plus wave in this type of material with a left-handed with a right-handed wave, then you have enhancement of transmission. And if you go with the other polarization, the minus, you have decay of the transmission. So you just enhance or decays, let's say, the transmission.
Mm-hmm. Okay. And in the previous diagram, when you just before the mixed phase, do you have a higher order exceptional point because it is?
No, it's not higher order. It's in fact we check this in the normal incidence that we have the degeneracy to see if it's higher order, but it's always order 2 in all the cases.
Okay, thank you. Very nice talk. Thank you.
Thank you.
That's great. Any more questions?
Hello, Sebastian. Can I ask one question?
Sure, please do.
Thank you. Thanks for the nice talk. So for this PT structure, when you have gain and loss, I have seen in some papers that they need also to put some passive layer in the middle. So is this the case in your study, or you don't need the passive layer?
No. We don't need a passive layer. Why you say? I'm trying to remember if I have seen papers that they put a passive layer in the middle.
I think because the coupling between the gain and loss, they can control it with the width.
In order to leave the gain, the cap, in order to avoid the coupling, you say. No, we haven't. We have tried, let's say, 3 slabs, but it is mostly to exploit the surface waves that they are at the interfaces, to exploit them in, for example, in sensing, let's say, but not for uncoupling. Probably for the okay, if we study more realistic systems, then we'll probably end up with the conclusion that it's helpful, that the medium layer is helpful to uncouple the gain and loss systems. But currently, we haven't tried. We haven't put any medium layer for all these results.
Okay. Yeah, because we recently with Sebastian, we did something with the flexural waves, and we have seen that we need this passive layer to have this coherent perfect absorber laser. If we don't have this passive layer, we cannot have the this lasing. And this, so my second question, like I see the amplitude of your eigenvalues is not extremely high. So you didn't consider the lasing operation?
We have not considered the lasing operation or the demonstration of the CPA laser yet. Still, we try to explore the eigenvectors and to no. The answer is no. We have not considered yet.
Okay.
But we see that it is possible, and by plotting the frequencies, the eigenfrequencies of the scattering matrix, and the frequencies, the imaginary part of the frequencies cross after the exceptional point, they cross the real, they go from the negative imaginary space, let's say, to the positive imaginary space, demonstrating the possibility that we have an exceptional point here, and actually a CPA laser. And this can be, depending on the input wave, it can be lasing of left-handed or of right-handed circular polarization. You can control the polarization of the lasing, and you can decide which polarization, the left and the right, will be in the absorber mode, and which one is in the laser mode, by controlling the input wave, but not yet explored in detail, let's say, or demonstrate.
Okay. Maybe one last question. Do you see any way how to generalize this for acoustic or elastodynamics? Maybe if you have some, I mean the chirality, because
I think I think as we said before, Martin Wegener, he had presented, he had chiral acoustics. He has presented a talk on chiral acoustics, and I think they are directly transferable, let's say. And also, I have seen some papers from Xian Zhang, for example, which is parity-time-symmetric acoustics, where they require the compressibility to fulfill the same condition like the one I presented here for the chirality, probably. So if you get chiral acoustics, I guess you will have an equivalent chirality parameter. So you have to impose some condition on this chirality, some extra condition besides the conditions on density and compressibility. And I suspect very similar effects. The only actual difference is that you have transverse waves here, and you have longitudinal waves. For example, in the case of only acoustics, I don't know what this can be, what this difference can bring, what difference this difference will bring into the system characteristics.
okay, thank you. Thank you.
Wonderful. So do we have any more questions for Maria? I particularly encourage young researchers to come forward with their questions, but of course also more senior people. Actually, I mean, regarding what you've said, Maria, even for just the case of pressure acoustic waves, there is this kind of Willis coupling, which is equivalent to bianisotropic media. I mean, and without moving to, you know, the realm of elastic waves, just at pressure acoustic waves, you don't call it chirality, but you have a so-called Willis coupling, which might actually generate similar effect to yours, just considering pressure acoustic waves in this kind of
Okay.
Okay, people from optics. I mean, I know that we have very clever people from optics in the audience. So if anyone wants to come forward with their question. Right. Last opportunity to take this unique opportunity to ask a question to Professor Kafesaki.
Okay, it's not unique. Anybody can send me an email with a question.
It's not unique. There is no uniqueness here. So you can, of course, then contact Maria by email or, you know, soon, hopefully, meet her in person at a conference when this horrible disease will be behind us. Okay, thank you very much, everyone, and especially Maria for this wonderful talk.
Thanks to you. Thank you very much for the invitation. It was a pleasure to see you after a long time,
Yeah.
even via computer.
And you know, I remember back in 2009 when Etopim was in Crete.
Ah, yeah.
It was absolutely lovely. It was absolutely lovely, this Etopim.
I enjoyed it as well. It was quite nice. Yeah.
Yeah.
Okay.
So people, might I remind you that in 1 week, no, not actually in 1 week, tomorrow we have the second time-varying workshop of the time-varying workshop series at Imperial. And with wonderful speakers. I can't remember who will talk, but they are just wonderful. Perhaps Nader and Geta and Matthias Fink. Well, random guess. And in 1 week, Bogdan, who will be our next speaker?
Pingsheng.
Wow. Guys, not to be missed. So tomorrow, wonderful event in Imperial with a time-varying media workshop, and in 1 week, Professor Pingsheng. So until then, stay safe. Bye-bye.
Bye-bye. Thank you.
Bye,
guys.
Thank you so much, Maria. Bye.
Thank you.
Bye, thank you.
Yeah, it is confirmed.
Bye.
Nader and Geta and Matthias Fink for tomorrow. This is confirmed by Paloma. So please don't miss this event. Tomorrow.
Bye-bye.
Bye.